Welcome back to week 4 of our course, Boltzmann Law, Physics to Computing. This is the third lecture. Now, in the first lecture, we laid out the rule for translating the classical picture into the quantum picture. So the classical spin with these two values, +1 and -1, in the quantum picture, the quantum spin gets replaced by this operator sigma, which has these three components, and when you measure you get only +1 and -1, but in general you have to use this matrix description, and you have an energy matrix from which you can get a probability matrix, and if you want to predict the values of a quantity S, you have to know the corresponding operator so that you can calculate this quantity. So in the second lecture we went through a specific example with one spin. Now what we'll be doing in this lecture and the next is we'll be talking about interactions, multiple spins. Okay. Now consider two spins, and if they were not interacting, then I guess the classical picture would be h1.m1 plus h2.m2, and the corresponding quantum picture would be h1.sigma1 plus h2.sigma2. So last two lectures we talked of just one spin. If there are two non-interacting spins, then it's easy. You just add the second one. And if you want to have interactions, then classically you would have J times this interaction term times m1 dot m2, and correspondingly here you would have a sigma1 dot sigma2. Now the tricky part though is, okay, if you write it out, you'll see all the components, h1x, sigma1x, etc. And here sigma1 dot sigma2 means sigma1x, sigma2x, sigma1y, sigma2y, sigma1z, sigma2z. And here I've written jx, jy, jz, because in general those three could be different, but what we have assumed here is it's the same j for all three components. Okay. Now the tricky part is that actually when you have two spins, this energy matrix is 2 square by 2 square. If it were n spins, it would be 2 to the power n by 2 to the power n. So it's a matrix in this 2 squared space. Whereas the matrices we had written down earlier, those were 2 by 2 matrices, these polyspin matrices. So the question is, how do we write down these two spin matrices which are 4 by 4? If we knew how to do that, then after that it's straightforward again. You have the energy matrix, you can calculate density matrix and then calculate any operator. So supposing we want to write sigma 1x, which means the spin of spin 1. So the rule is, okay, I'm thinking of the two spins as 1 and 2. So for 1, I want to know what is sigma x, and for 2, that's where I don't really care. And that's where you put the identity matrix. So the corresponding operator then is sigma x and I, but you have to take the Kronecker product of the two. So, and this is what in MATLAB or Python you'd use a command like this. Now how does this Kronecker product work? It's not a matrix product. Matrix product, if you took a 2 by 2 and multiply by 2 by 2, you would have got another 2 by 2 matrix. But when you take this Kronecker product or tensor product, you actually get a 4 by 4 matrix. So sigma x is this one, I is that one, and when I take the Kronecker product, I'll get a 4 by 4. Now how does that work? Well, it goes something like this. Here you have a 0, so that's this 0, and you multiply it times this matrix 1 0 0 1. Similarly here you have a 1, so it multiplied by again the same matrix. So the matrix on the right kind of goes in everywhere, but here it's multiplied by the element you have there, here it's multiplied by the element you have there, and here by again the element you have here, and so on. So that's how you write the Kronecker product. And of course if you're using MATLAB or Python, that's what the computer would do for you. So if you try to now write this out, what will happen is in this corner it's 0 times this, so you basically get 0 0 0 0. Here it's 1 times this, so you get the sigma x back. Here again you get this matrix back, and here you get a 0. So that's what sigma 1x would look like. Now, if you want sigma 2x, which means I want the x component of the spin 2, then you see it's a little different, because now, again, I've numbered in my mind these spins as 1 and 2. So the first one, I don't care now, because I want the spin on 2, so I put an I there. And the sigma x, that's where 2, that's where I put a sigma x. So now I have to take the Kronecker product, but in the opposite order, I cross sigma x. So I is this identity matrix, that's sigma x, and I have to take the Kronecker product. And the principle is the same. So you take this, multiply it by 1, and put it here. Take this, multiply it by 0, and put it there. Take this, multiply it by 0, put it there. Take this, multiply it by 1, put it there. Point to note is, those are not the same matrix. They are two different matrices, sigma 1x and sigma 2x. One represents the x component of x spin on spin 1. This one is the x spin on spin 2. Now, if I multiply them, sigma 1x times sigma 2x, I'll get this quantity. This is a straightforward multiplication matrix. This now is straightforward matrix multiplication. So I take a 4 by 4 and a 4 by 4, multiply, I get 4 by 4. What if I multiply them in reverse order? Sigma 2x times sigma 1x. Again, the details are different, but you end up with the same matrix at the end. You see? You'll notice that it doesn't matter which order you multiply, you get the same matrix, which in, I guess, you'd say, that's what you technically say, that the two matrices commute. And what you get is actually what you'd have got if you had just taken sigma x and taken a Kronecker product with sigma x. That would have given you exactly the same answer actually. Now, this is then what we could identify as the operator for m1x, m2x. So experimentally, if the question we are asking is, what is the probability of measuring, what is the expectation value, average value of the measurement of x spin on spin 1 and x spin on spin 2? And we look at the product. So when I measure the x spin of spin 1, I get +1 or -1. X spin of spin 2, again +1 or -1. And I want to know what is the average value of the product. Well, this is the operator I should be using. Now, what if I wanted to know the x spin on 1 and the y spin on 2? Well, then the operator would be like sigma x cross sigma y, or you could write sigma 1x, sigma 2y, and sigma 2y, sigma 1x. You can multiply them in either order and you'd get the same answer. So how would you write sigma 1x? Well, it's sigma x, Kronecker with I. Sigma 2y, well, it's I, Kronecker with sigma y. And again, the rules that we discussed about how you take Kronecker products, you can easily check it out. This is what you'd get. And so when you multiply, you'll get that quantity. And if you multiply the two in reverse order, sigma 2y first and sigma 1x later, well, you still get the same matrix. And this is exactly the matrix you would have got if you just Kroneckered sigma x, Kronecker sigma y. So this is how you would write again the operator for answering questions about measurements of x spin on 1 and y spin on 2. Now you might say, well, what if I want to know the x spin and y spin, but on spin 2, both on spin 2? Now this, if you remember from our first lecture, this is something quantum mechanics says you cannot do, because you can never measure the two components on the same spin. And indeed, if you try to write the operator for this, you'd get in trouble. You could see, if you do sigma 2x, that is I cross I Kronecker with sigma x, you get this matrix. Sigma 2y, again I Kronecker with sigma y, and you get that matrix. And you multiply the two, you get this. But if you multiply the two in reverse order, you get exactly the negative of this. You don't get the same one. And what that means is there'd be no unambiguous way of defining a proper operator for that question. And that is a question you're not allowed to ask. And I guess what you could show is that what this matrix is I sigma 2z, and this is actually minus I sigma 2z. And this is related to that identity where I had mentioned in lecture 1, that sigma x sigma y is actually equal to I sigma z. And here, as you notice, all our measurements are on spin 2, and spin 1 is just sitting there, it's just going along for the ride. And so basic results, although we are writing 4 by 4 matrices, it's basically what you'd have expected for one spin. But the bottom line is, we are not allowed to ask this question because the corresponding operators do not commute. Okay. So that's the bottom line, that when operators do not commute, well, that is something experimentally you couldn't ask. You couldn't measure those two things simultaneously. Whereas things like m1x, m2 to y, which is what is the x spin on 1 and y spin on 2, well, that's fine because these are two separate spins. You could measure any component of one and any component of another. That is fine. And so they can be measured simultaneously. And sure enough, the corresponding operators commute. Okay. Now, in terms of getting back to the original problem, that if you had the two-spin problem with interactions, we had this energy matrix that's given by this expression. Now what we have seen is how to write sigma 1x, sigma 2x, sigma 1y, sigma 2y, sigma 1z, sigma 2z. Each of them are now 4 by 4 matrices. And we have these matrices. So basically we have all we need to write down these. And in the next lecture, we'll work out an example in a little more detail to see how you apply it. But the point is, we now have the matrices we need to write this down. And once you have H, you could find this, do the exponentiation, and you'd get the density matrix or the probability matrix. And we have also seen how to write the operators for any question you want to ask. And then you could take the trace and find the expectation values. Indeed, in principle, this is how you could talk about an n-spin system also. If you had n spins with interactions that are called two-body interactions, in the sense the interactions involve just two spins, which is usually what you see, then the general expression would be something like this. And each one of these sigmas would actually be a 2 to the power n by 2 to the power n matrix, you see? In the sense that supposing you had a 4-spin system and you want to know what is sigma 2x, well then the sigma 2x matrix would be like a Kronecker product of I, sigma x, I, and I. So you've got I is the identity matrix and sigma x is the polyspin matrix, spin x matrix, and you take 4 of them and your Kronecker product. And when you take 2 of them and your Kronecker product, you get a 4 by 4. You take another Kronecker product, you get 8 by 8. Another one, you get 16 by 16. So these matrices that would appear in a 4-spin system would all be like 2 to the power 4 by 2 to the power 4. And that's how you can write down, in general, in principle, the Hamiltonian matrices for an n-spin system, from which again you can get your density matrix and then find the expectation values of operators. So in principle, that's all there is to it. In practice, of course, the problem gets huge as n gets bigger because of this exponential problem that I had mentioned before, that as n grows, 2 to the power n grows exponentially. And that is what makes it practically difficult to deal with large quantum spin problems in general. And that is, in a way, the basic rationale for building a quantum computer. The idea is that if you have a problem that can be cast in this form, then the thing is, a direct calculation would get exponentially harder. But if you could build a quantum computer, the computer could calculate it for you. And so for example, if you had a 40-spin system, then the direct calculation would involve matrices like a trillion by trillion. But a 40-qubit quantum computer could calculate it for you. That would be roughly the rationale. Okay. So what we'll do next is then we'll look at an example of a 2-qubit system and how to calculate expectation values and write down Hamiltonian operators. Thank you.